Hello, everyone, and welcome to our webinar. Our topic today is titled Connection Design Solutions for Wood Frame Structures. My name is Karen Beebe, and I will serve as moderator for the session. Our speaker, Bob Cuserk, and I both work for APA, the Engineered Wood Association. APA is a nonprofit trade association representing manufacturers of a variety of common structural engineered wood products. In addition to quality verification and product testing, APA conducts research to improve engineered wood construction systems and educates users and specifiers on the product's proper use and potential applications. Before we start today's webinar, I need to cover some housekeeping details. Bob's presentation will last about 50 minutes. To ensure that everyone can hear it clearly, we have muted all participants. We do encourage you to submit questions by typing them into the questions pane on the control panel on your screen. We should have time to answer most questions, but if we run short, we'll be sure to post a Q&A summary on our website, along with a recorded version of today's program. We should have those posted in a week or so. I'd also like to note that today's webinar is approved for AIA and ICC continuing education credits. About an hour after the conclusion of the webinar, an email will be sent to each attendee. It will include a link where you can get customized AIA and ICC certificates of completion. Our presenter today is Bob Cuserk, Engineered Wood Specialist for APA based in New Jersey. In that role, Bob works with designers, building officials, and builders on the various engineered wood products that are used in buildings today and consults on engineered wood use in construction applications. Prior to joining APA, Bob spent 20 years as an engineer providing technical support for a major manufacturer of engineered wood products. He is a licensed professional engineer in 10 states and received his Bachelor of Civil Engineering from Villanova University and a Master of Civil Engineering from the University of Delaware. For those of you just joining us, welcome to APA's webinar on the topic of connection design solutions for wood frame structures. I will now turn the microphone over to our speaker, Bob Cuserk.
Thank you, Karen, and thank you all for joining us today. As Karen mentioned, in today's webinar, we're going to focus on connection design and considerations with wood construction. As Karen mentioned, this course is registered and approved by AIA, and credits earned will be reported to AIA upon completion. As such, it does not include content that can be construed to be an approval or endorsement by AIA. For many building designers, designing sound wood connections can be a daunting task. Yet connections are one of the most critical items in any structure and require a good understanding if one is to develop sound, aesthetic, and/or cost-competitive solutions. Today's learning objectives are to first discuss code-compliant connections, provide an overview of the design process for dowel bearing connections, discuss the effects of expansion and shrinkage and its importance in wood connection design, and highlight the proper specification and detailing of steel connectors used with wood. Before we get started, we have a poll question, so I'd like to turn this over to Karen to run the poll question and see who we have attending today.
Thank you, Bob. As you can see, the simple poll question, what is your profession? Please select one, architect, engineer, building official, building designer, or other. We'll go ahead and close that poll now and share the answers. Excellent. It looks like we have 75% of you are engineers, 8% architects, 5% building officials, 3% building designers, and 9% other. Back to you, Bob.
Okay, thank you. That's always good to know who's in our audience or who we're talking to. So our agenda today is achieving the aforementioned learning objectives. For this webinar, we're going to review our wood basics and connection philosophy and how it affects connection design, serviceability, or the environment that the wood will be used, some different connection types, provide an overview of dowel bearing connections and what is involved in designing these connections, review some wood structural panel connection basics, and lastly, discuss the importance of using proper corrosion resistant connections to ensure that the connections perform through the life of the structure. So let us start with wood basics and how they can affect connection design and details. We will first examine some of the basic properties of wood and the strength direction of wood. Understanding the strength direction of wood will build the foundation that allows us to address the challenges and opportunities that exist with wood construction. We need to understand that wood, like all material, moves and how this wood movement affects connection design. It's best to think of wood as being similar to a bundle of straws. When compression is applied to the ends, the straw bundles are strong and resist loads very well. Applying tension to the straws also develops considerable strength in the straw bundle. However, hanging onto the ends becomes more of a challenge in designing a suitable connection. If loads are applied perpendicular to the longitudinal axes of the straws crush easily because of the weaker radial alignment orientation of the cellular walls, or pull apart where tension is applied to the straws in the bundle. This illustrates the anisotropic nature of wood, different strength properties in 3 different directions, longitudinal being the strong direction, tangential a little weaker, and radial being the weakest of the 3 directions. As we said, wood grain is strongest and likes load applied as compression parallel to the grain. Structural designs that capitalize on this idea are very economical and attractive and consistent with wood's heritage of the tree and the forest standing tall and strong. Moreover, compression connections of wood are usually the easiest to design and detail. Wood's weakest link is tension perpendicular to grain. Tension perpendicular to grain happens when you apply loads that try and pull the wood fibers apart. This type of loading often leads to sudden catastrophic failures and should be avoided at all costs. Awareness of how the wood is being loaded is all that is needed to avoid this issue. The solution is detailing to avoid perpendicular to grain stresses. Some factors that influence tension perpendicular to grain loads include notches, large diameter fasteners, and hanging loads. The last idea we'd like to understand about wood connections is that wood likes to see loads spread out. Concentrated loads should be avoided when possible, as it could easily exceed the bearing or tensile capabilities of the wood. It is better to spread the load out with small multiple fasteners in place of one large fastener, as this approach builds in a degree of redundancy, as I'm now trying to pull multiple straws apart or have multiple bearing points at each connector. Now that we have a basic understanding of wood as a material, we'll start looking at some connection design and detailing. I'd like to start by noting that a lot of the details and examples you will see today can be found in APA's Glulam Connection Detail publication. Proper connection details are important to the structural performance and serviceability of timber frame structures. This illustrated guide shows correct connections as well as common connection errors involving glue laminated timbers. The concepts shown can also be applied to most wood applications. Also, the United States Department of Agriculture and Forest Products Laboratory Wood Handbook is a great resource that summarizes information on wood as an engineering material. More in-depth wood property explanations and design considerations can be found here. This publication is available as a free download on the Forest Products Laboratory webpage. Additional resources that are always helpful to the designer include the International Building Code, International Residential Code, ICCES Code Acceptance Reports, and APA product and system reports, and of course manufacturer literature information are always good resources. The environment that wood exists in will affect the ability of the member and connector to perform over the life of the structure. Let's review some different serviceability factors and how we can accommodate them in connection details. This image is a good example of how wood cut from the different areas of a tree will react to moisture. Trees in their natural growing state are saturated with water. As soon as the tree is cut, the drying process begins as it can no longer take in water. As water dries, it tends to shrink tangentially, perpendicular to its grain. Shown here are some of the most common shapes used in wood members. This image illustrates the potential dried shapes of these materials as it relates to the growth rings of the tree and the location of the cut. You will note that depending on where the lumber is cut from the tree relative to the tree growth rings, it may be more susceptible to cupping or dimensional changes in the height or width of the member. Wood is a natural material that moves in response to varying environmental conditions, just like other building materials. The main driver for the dimensional change of wood is moisture. Allowances must be made to accommodate this movement, particularly in connections. Wood is very sensitive to moisture change and alters its cross-section dimensions in response to the gain loss of moisture in the wood cell walls. Shrinkage can loosen bolted connections or increase instability in hangers. Swelling can deform connection hardware and cause other geometric problems. Day-to-day temperature changes generally don't play much of a role to disrupt the connection's life. However, extreme changes in short periods of time can, especially if there's a lot of metal hardware in the connection, as metal and wood have very different thermal expansion coefficients. This difference can cause some grief if not taken into account for extreme conditions. Moisture also affects the strength properties of wood. We'll review this aspect in greater detail when we take a look at dowel bearing connector design. Moisture has a great impact on how wood performs. Designing a connection with the equilibrium moisture content of the wood must be taken into account. One big misconception is that the equilibrium moisture content of wood and the relative humidity of the atmosphere are the same, when in fact equilibrium moisture content is calculated using constant temperatures at varying relative humidity. As you can see from the graph, a relative humidity of 90% does not produce an equilibrium moisture content of 90% in the wood. Rather, using the table, a temperature of 88 degrees, for example, at 90% relative humidity equals about 15.7% equilibrium moisture content in the wood. The above chart shows how the equilibrium moisture content changes with both temperature and humidity. Ambient conditions drive the equilibrium moisture content of the wood also. The map taken from the USDA Wood Handbook shows equilibrium moisture content for wood in various parts of the country. This table shows the variation by month of the equilibrium moisture content for wood exposed to the outdoors for various locations in the country. We can see by the table that the equilibrium moisture content variations can occur across a construction timeline. Changes in equilibrium moisture content translate into issues that must be accommodated for in design, such as dimensional change. Another consideration is using wood in proximity to other materials. Concrete is porous and wicks moisture. Good detailing will use separators like base plates or standoffs, etc., to permit wood to be used without direct contact with concrete. One might think that this solution works. However, the flat concrete surface may allow the wood to contact standing water even if a vapor barrier is installed at the base. It is not encouraging to the long-term welfare of the wood. It is best to use connecting hardware that breathes and drains. Notice the cap flashing on the beam's top edge to discourage rainwater from being absorbed into the top of the wood section and direct water away from the wood. If water does get in, you need to design connections that let it out and let the end section breathe. Trapped moisture quickly leads to fungal growth and decay under the right conditions. Details often include weeps and vents in shoe-type connection hardware to facilitate venting, which can be fine. But be careful, sometimes weep holes clog. Make sure the connection allows the water to drain. Here is an example of a good bottom connection using an elevated base plate. This detail is aesthetically pleasing and keeps the wood from sitting in standing water and helps to avoid decay. Just as with columns, wood beams on shelves or wall beam pockets can also wick moisture, so the end of the beam should not be in direct contact with the concrete. The bearing plate distributes load and keeps the beam from direct contact with the concrete. Steel angles or straps can be used to provide uplift resistance if needed. It can also provide some lateral support for the member. Keep in mind the same provisions for concrete must be made for masonry. Here are some examples where wood is in direct contact with masonry. These conditions create a potential for decay and failure of the product. So let's take a look at some of the different connection types for bending members. The first most basic connection is direct bearing of the beam. Keep in mind we said designing connections is all about the details, so let's take a look at some common direct bearing conditions and some details that make a difference. A basic example of direct bearing connection is simply to bear the beam directly on a steel plate, or with the use of a top flange hanger where the beam bears directly in the hanger saddle and the hanger bears directly on the top of another beam or a supporting member. Direct bearing for the beam and direct bearing of the hanger. But even with these type of bearing conditions, there are some details to consider. First, if the beam is bearing on a concrete ledge or pocket wall, recall that there must be a half-inch airspace between the wood and the concrete, or a vapor barrier must be used. In the example on the left, the steel plate serves as a vapor break. In these details, a common error that can happen is notching or overcutting the beam of bearing. This condition results in cross-grain tension stresses that can cause splitting at the inside corner or at the interior face of the bearing due to shear stress concentrations. Again, think of those straws splitting apart. In glulam and structural composite lumber, bottom beam notches at the end should never exceed the lesser of 1/10 of the beam depth or 3 inches. Notches can be checked using the notch beam formulas found in the NDS 5.4.4, but reductions are severe. The 14-inch beam with a maximum notch of 1.4 inches results in a reduced shear capacity of about 28%. Let's look at some other direct bearing connections. Similar connections can also be found when members are sloped, such as in roof systems. While all these connections are pretty basic and simple, there are a couple things to think about when these connections can go wrong. Most importantly, these include the weakness of wood in the cross-grain tension stresses and the effects of moisture. Overcutting the beam at the base can induce cross-grain tension stresses, as shown in the detail on the left. Also, similar overcuts at intermediate or top bearings of a slope beam can also result in similar stresses, as shown in the detail on the right. For these details, it is best to use a slope bearing connector. Heavy concentrated loads suspended from the bottom of beams can also induce tension perpendicular to grain stresses and may cause splits, as shown. Sufficient compression would exist to develop the full bearing resistance to the beam hanging load. The better solution would be to wrap a sling over the top of the beam, placing the top of the beam in compression rather than some interior portion of it, or extend the support plate into the upper half of the beam above the neutral axis with extended plates. I will mention that this is not intended to apply to lightly loaded members, such as from floor joists attached to the main beam with light gauge nail-on metal hangers. I mentioned the simplest of beam connections is to directly bear the beam onto another beam, column, or wall. But even with this, the simplest of concepts can have downfalls. Take, for instance, the photo of the beam on the left. This beam is bearing on a double 2-ply plate, which is bearing on 4 studs. By all accounts, this beam is pretty large. It's 3-ply, 24-inch deep LVL. In this detail is constructed, the allowable reaction will be controlled by crushing of the 2-by plate. Consider the allowable crushing for an LVL is generally about 750 psi loaded in the tangential direction versus 425 psi for, say, an SPF wood plate being loaded in the radial direction. As opposed to bearing directly on the studs loaded on the longitudinal direction, which would be the strongest strength of the wood, we have loaded the detail in the weakest direction. We can improve this detail by framing the studs directly to the bottom of the beam where the crushing of the LVL now controls. This will increase the allowable bearing for this detail by approximately 75%. Since wood is stronger in the parallel to grain direction, this bearing could have easily been improved by framing the studs directly to the bottom of the beam with king studs on the sides to provide lateral support. Bolt placement can also play a role in direct bearing hangers. Recall, when we talked about the effects of moisture, we talked about wood wanting to shrink or swell based on its moisture content. In a direct bearing connection, the intent is for the beam to rest in the hanger, supported by direct bearing in the saddle. If bolts are placed in the upper half of the hanger, the beam can shrink away from the seat and initially become supported by the bolts. This results in the beam being supported by the bolts until splitting occurs as the beam looks to resettle into the hanger. Here you see that exact thing happening at a Cabela's store. The beam was initially seated on the support angle, but if you look closely, you can see that a business card can now be slid between the beam and the bearing location at the bottom of the beam. This beam is experiencing stresses at the bolts that it was not designed to handle and is starting to split as the beam looks to settle back onto the angle. These are some good details that work in that they don't notch the beam, and these connectors also provide the ability for the wood member to move in the hanger as slotted hardware or bolts is allowed to permit dimensional changes of the wood without restriction. Hybrid connectors share attributes of direct bearing of the beam seated in a hanger and dowel bearing type connections where the hanger is attached to the face of a beam with nails or screws. However, recall that tension perpendicular grain is wood's weakest link and should be avoided. To avoid these stresses, the dowel type fastener should be installed above the neutral axis or center line of the supporting beam. Installing a hanger that transfers a large load in the supporting member can induce cross-grade tension stresses that can result in splitting of the supporting member. There may be times that a concealed connection may be desirable. This is perfectly acceptable, as this connection isn't fundamentally different than the connections we have just reviewed, and the same wood philosophy should apply. This means providing full bearing and designs that allow the product to move. The suspended beam may be dapped on the bottom for a flush connection. The pins may be slightly narrower than the suspended beam, permitting plugging of the holes after the pin is installed. Note that the kerf in the suspended beam must accommodate not only the width of the steel plate, but also the increased width of the fillet well. This is also an insulating detail that is applicable in heavy timber fire-resistant design. Burying the metal underneath the insulated layer of wood prevents the metal from overheating into a plastic state during a fire event. You see American Wood Council's technical report calculating the fire resistance of exposed wood members, TR10, for additional details. This document is a free download on the American Wood Council's webpage. For taller beams, ladder stability may also be required at the top of the beam. It may be desirable to install guides at the top of the beam to provide this lateral stability without installing restrictive connections. This type of connection ensures that the compression edge of the beam is still laterally supported, but no bolts have been used at the top, so the beam is free to move and avoid stresses that may cause splitting. Beams supported on columns aren't much different. Provide full bearing and a connection that allows the beam to move. However, in this example, the only movement that we need to consider isn't from moisture. Loaded beams will rotate at the bearing as a result of the deflection of the beam, so the designer should consider this and detail connection that allows for this rotation. The detail on the left allows for the movement of the beam to grow from moisture and allows rotation at the top of the beam for deflection. As an alternative, smaller plates will transmit the desired forces but not restrain the wood from its natural movement. However, note the slotting of the holes in the upper plate allow the beam to move, otherwise splitting may occur due to beam rotation as the beams deflect under load. It is sometimes desirable architecturally to conceal the connection at the base of the column as shown on the left. In any case, it is crucial to detail this connection to minimize decay potential. This detail is similar to other details already seen, but with the floor slab poured over the top of the connection with concrete in direct contact with the wood, this will cause decay and is not a recommended detail. On the right, since this is the bottom of the structure, it's conceivable that moisture from some source might run down the column. Experience has shown that base plate details in which a steel shoe is present can collect moisture that leads to decay in the column. Bucket-style hardware also causes a lot of grief for wood connections if they are not properly vented or drained to let moisture and water escape. Alternate details allow water to drain at the column base. Details that include a bottom bearing plate and angles are acceptable, as well as a simple bow and a bearing plate for a concealed look. Even when we get all of our detailing correct, sometimes decisions are made in the field. And by the way, the designer of this detailed a loose steel plate. However, the contractor felt grout would still work just as well. However, grout, like masonry or concrete, should not be in direct contact with the wood. So let's move on to another common connection used with structural composite lumber, which is the connection of multiple individual plies to fabricate a wider built-up beam. This is very common with 1 3/4 LVL, glulam beams, and dimension lumber. Multi-ply sections usually need some type of connection if the plies are to act in composite form or as a single member. This is particularly important for beams. Side-loaded beams can be specified with a solid wood section like glulam or white LVL, which will overcome the typical issue of overloading the outer ply of a multi-ply edge-loaded beam. However, there are many situations where multi-ply beam section makes sense and is preferred, especially in renovation work, where it is easier to work with small plies to build up a wide beam in place. However, these connections must be designed properly. In a top-loaded application, the load is applied to the build-up beam from a wall or post above. In theory, if the load is bearing equally on all plies, and they are identical in strength and stiffness, the load should be equally distributed between plies without any beam-to-beam connection. However, as the actual positioning of loads are seldom exactly as planned, a minimum connection between the plies is necessary. APA technical topic, Connections for Build-Up Glulam Beams, TT-011, addresses these concerns and provides guidance for these connections. Also within the APA technical topic, you will find connection details for flush beams loaded on the side. This table provides different connections for uniform side-loaded beams specified for different glulam member species and connections. Similar to glulam beams, there are multi-ply connections for LVL that should also be considered. These connections can vary slightly between manufacturers, usually depending on wood species they may be using. For these connections, you should consult the manufacturer-specific literature for assistance to design appropriate connections. In light frame residential construction, the most common connection that you will likely encounter is a pre-engineered, off-the-shelf metal hanger. These hangers are very useful products and save considerable connection design and construction time. With published capacities and corresponding fastener specifications, they're easy to select and specify. Generally, these hangers come in two varieties: a top flange hanger, where the load is transferred into the supporting member through the top flange of the hanger, and a face mount hanger, where the load is transferred to the supporting member by fasteners installed on the face. Examples of each are shown in this photo. These hangers are product specific with published capacities based on the specified nail or screw shown in the manufacturer literature with adjustments for alternate fasteners. When in doubt, it is always best to fill all the holes, as many fastener capacities are based on using all the holes. However, sometimes capacities can be based on reduced nailing with a reduced capacity, so the hanger can be checked by the designer and nailing can be specified in these instances. As with any connector, ensure the proper specified fastener is being used. Make sure the fastener penetration and the fastener is very important. Remember, an 1.5-inch nail does not have the same capacity as a 3-inch nail. Presently, there are many hanger choices available to the designer to accommodate a myriad of applications. Reviewing these numerous choices is beyond the scope of this presentation today, and we recommend you consult with hanger manufacturers in selecting proper hangers. Their literature provides capacity of the hanger, nailing, and other relevant installation details. In addition to their catalogs, they may also have software applications that can help you in making choices. Additionally, many joist and structural composite lumber manufacturers include hanger selection as part of their software to assist in selecting an appropriate hanger. But even though these hangers are proprietary, there are some generic details that need to be considered. This photo shows the importance of using the correct hanger for the product. I-joist hangers are specific to the joist and not only provide the support for the member, but also provides lateral stability for the product. Joist hangers that do not support the top flange of the joist require a web stiffener for lateral restraint. In the above photo, these are not the correct hangers. Not only do you not have lateral support, the hanger being wider than the seat will affect the vertical capacity of the hanger, as localized bending of the hanger seat will result. Regarding the use of these hangers, as you saw in the previous slide, there are some general details that need to be followed when using hangers with an I-joist. This also applies if the I-joist is the supporting member. If using a top mount hanger, you need a backer block installed tight to the top flange to prevent rotation, or you will need a backer block for the attachment of a face mount hanger. In addition to backer block placement, you will also need to consider the connection of multiple joists together to support the load. This is similar to what we just discussed with multi-ply LVL, glulam, or dimension lumber. I-joists will need to be packed out with filler blocks so that the load can be shared between the joists. These filler block requirements change with the joist series to correlate with the joist flange width to pack out the distance between the webs of the joist. Filler block details can be found in the joist manufacturer's literature. Beyond the prefabricated connectors that we have discussed, the most common connection that is likely to be specified is a dowel bearing type of connection, where the connection relies on bolts, screws, or nails to transfer loads between members. These can be some of the most intense calculations. Here are some examples of dowel bearing mechanical connections made in a variety of ways. Some are using only wood, some with hardware, some with fasteners. Connections typically test the designer's skill to arrive at a safe, aesthetic solution. Choice of connector system is critical to the connection's ductility, strength, and performance in service. For most connections, we're going to be looking at mechanical, dowel-type fasteners, nails, screws, bolts, and lag screws. Power driving fasteners are not new and have their own unique concerns that we will discuss, including nail nomenclature, contact or clamping of materials, thin galvanizing, and overdriving. Let's start with nail nomenclature. Unfortunately, there is no standard name, size, metal, or otherwise for nails. System manufacturers have their own tables, etc., which varies amongst manufacturers. Even looking at a 10D nail, we have common, box, sinkers, each with their own diameter. Further looking at the different types of nails, we said there are many variations of a nail, and they're shown here with a variety of their names. Nail capacities are tabulated for only some of them, such as box and common nails, since these are standardized to some degree based on their shank diameter, which is the driver of the capacity tables. Should avoid problems by specifying the penny weight, the type, diameter, and length. Example, a good specification is a 10D common 0.148-inch shank diameter by 3-inch shank length. This is the best way to ensure that you get the nail that was designed to be used on your projects. We mentioned that there are different sizes of nails that could be specified to get the intended capacity of the connector. We also need to consider some other factors. First being contact or clamping. Consider that a hand driving a nail also clamps the material together as you drive the nail, whereas a power-driven nail uses velocity to drive the nail, so it doesn't have that same clamping action that pulls the materials together. So in using a power-driven nail, the installer must make sure the materials are clamped together when driving the nail. We should also consider that power-driven nails generally have thin galvanizing that may scrape off when driving the nail that can lead to rust if exposed, so they should be covered relatively quickly. Lastly, one of the most common concerns is overdriving nails. There is a correct way to adjust the nailers to ensure the nail is driven properly and consistently. It is not to increase or decrease the nail pressure on the nailer. Most connectors are based on a standard specified connector, such as a 16D common nail, for example. That is not to say that that is the only fastener that can be used for the job. The International Staple, Nail, and Tool Association has an ICC ES Code Report 1539 that has values for staples and other power-driven fasteners that allow for the interchangeability of the fastener. You can consult their code reports for these alternate connectors. When it comes down to dowel bearing fasteners design, these typically require an engineered solution. The National Design Specification for Wood Construction, NDS 2015, provides guidance for the design and specification for dowel bearing connections that we will review here. In designing a dowel bearing connection, equations have been developed as part of the 2015 NDS for 4 possible yield modes that dowel fasteners can take on. These encompass the 4 modes of failure: bearing, fastener pivoting, fastener yield at 1 hinge point, and 2 hinge points. This results in 6 equations that represent these failures. You can see these failures graphically represented in this slide. Mode 1 is crushing of the wood member. Mode 2 is pivoting of the fastener in the wood. So both these modes only consider wood failure, whereas the other modes consider failure of the connector and is dependent on the strength of the fastener. Mode 3 is bending of the fastener at 1 location for the single shear connection and 2 locations at the double shear connection with 3 members, whereas Mode 4 is bending of the fastener at 2 locations for single shear and 4 locations for double shear. For simplicity, let's take a quick look at the equations for a single shear connector of the 2 members consisting of a main member and a side member. The yield and factor equations are shown here and can be quite cumbersome, but all 6 yield modes will need to be considered to determine which failure mode governs. Additionally, we will need to consider reduction terms appearing in the denominator of the NDS yield equations. These can vary by the dowel size. So let's look at how to calculate the capacity of a 1-inch dowel connector. That could be a bolt or a lag screw. in a single shear connection with a 3.5-inch main member and a 1.5-inch side member. We'll assume both wood members have a specific gravity of 0.5, which would account for a typical Doug fir material. We would start at table 12.3.3. We find the Dowel bearing strength of 5,600 psi for a 1-inch fastener in parallel. Take a note at this table how the Dowel bearing strength changes for the different diameters when considering the strength perpendicular to grain. The yield equations you will use are the same for perpendicular to grain, but the Dowel bearing strength differs and is fastener dependent. In the interest of time, rather than going through the equations, I assume we can work through the math and calculate the factors and the design values for the 6 different yield modes. In doing that, we find that mode 2, fastener pivoting, governs the design and provides a capacity of 1,827 pounds for this fastener. Now that we worked through that, I think it's time to take another quick breath and we digest what we've learned and pass it to Karen for our next poll question.
Thank you, Bob. Tension perpendicular to grain can be caused by notches in the beam, hanging loads, large diameter fasteners, or all of the above. We'll be closing the poll in a moment here. All answers should be in. And 93% of you said all of the above, 5% hanging loads, and 1% notches in the beam. Back to you, Bob.
Okay, thank you. It looks like we're doing pretty good on these poll questions. The answer to this question is all of the above. Recall that notching on the tension side of the beam, hanging large loads below the neutral axis, and use of single large diameter fasteners compared to multiple small fasteners can all produce cross-grain tension stresses in the member. So, returning to our Dowel bearing connector calculation, we found that was a lot of work running through those formulas, calculating 6 equations to determine which yield mode governs the design of the connection. Fortunately, there are tools to make this a little easier for you, and they've already done a lot of work for you in NDS. So the first resource will look at NDS itself. Tables 12A to 12D provide lateral design values for the different connectors in different applications, including single shear, double shear with wood, and steel side plates. So let's go back to our example of a single shear 2-member connection with both wood of the same specific gravity. To this, we would refer to Table A, which shows that for the load parallel to grain with a 3.5-inch main member, a 1.5-inch side member, and a 1-inch bolt using Doug fir 0.5 G, we find the capacity is 1,830 pounds, similar to the 1,827 pounds that we previously calculated by hand. But keep in mind, like any table, there are limitations based on the assumptions used to generate the table. Biggest assumption that may affect the designer is that this table assumes both members to be of identical specific gravity. In the event that you have woods of differing specific gravity, you would need to use the lower specific gravity to calculate the capacity using the table, or you would go back to calculating the capacity using the yield limit equations. Additionally, there are software options that are readily available to the designer. Many can be found online with a simple search. One is from the American Wood Council, which can be found on their webpage. As you can see, if we run our example through this calculation, it generates the 1,827 pound capacity for a yield mode. These online calculators also afford the flexibility to input different member species for the main and the side members. So now that we have the connection of the member, the capacity of the member, we're really not done yet. As we mentioned earlier, there are several factors that can influence the design capacity of the connector. These are listed as adjustment factors in NDS table 11.3.1. These factors generally reduce the capacity of the connector that we just calculated. The first factor that affects the design capacity is the duration factor. The load duration factor is not probability based, it is a material property of wood. Duration of the load is the ability of the wood to resist higher stresses when loads are applied for a short duration of time. In other words, wood has a higher strength when loaded is applied instantaneously and removed. than it does when the load is applied for a long period of time. This allows us to increase the allowable for short duration loads such as snow, but also requires us to reduce the allowable for permanent loads such as dead load. The appropriate factors are shown in this table. Most commonly, the designer would consider a 15% increase allowable for snow loads or 60% for wind loads. Connection strength also varies with wood moisture content, and the NDS has provisions to this effect, applying a wet service factor C sub M that affects connection values. Two conditions of moisture content at fabrication and in service are important, whether the wood is less than 19% or greater than 19%. The designer must assess the environmental situation to see which occurs and when. At moisture content levels above 19%, wood is more elastic and wood strength properties reduce somewhat. So let's first consider if the fastener installed is in a dry material and is used in service as a dry material. There's no adjustment factor, and you'll see in the table that C sub M equals 0. However, if the material is being used in a wet condition, greater than 19%, there is a 0.7 reduction required for lateral and withdrawal for screws and 0.25 for nails. But also note that there are reductions required for dry use service conditions if the fastener is installed in wet wood. In this instance, the lateral load adjustment factor is 0.4 and 1 for withdrawal for screws and 0.25 for nails and spikes. However, there's a footnote provision that provides some relief for lateral loading, allowing a reduction factor of 0.7 for fasteners less than 1/4 inch. That would then lead us to conclude the C sub M for lateral load equals 0.4 for fasteners greater than 1/4 inch. Yes? Fortunately, no. The footnote number 2 continues to state that for all fasteners, C sub M equals 1.0 if there is only one fastener that you're considering, or two or more fasteners placed in a single row parallel to grain, or the fasteners are placed in two or more rows with parallel to grain with separate splice plates for each row. So in this regard, there's additional relief that can be gained, but it requires an understanding of the condition when fasteners are installed, or in the anticipation of the conditioners when fasteners are installed, and how they will be in dry use service. Temperature of the wood can also affect the design values when wood is exposed to sustained temperatures. Let me emphasize, these are for in-service temperatures. Generally, the in-service temperature is less than 100 degrees Fahrenheit, so this is rarely a factor unless you have a specialty building where you have very high in-service moisture content or high temperature factors. The group action factor provided in the NES for connections involve large diameter fasteners often causes a lot of confusion. This factor accounts for load distribution with the connection. Nominal lateral design values for bolts with D less than or equal to 1 inch or lag screws in a row are multiplied by this group action factor. There are two ways to determine the group action factor. You can use the tables in NDS, or you can again calculate your own group action factor, especially if they're outside the tabulated range.
As we launch the fourth question and get ourselves back on track, the wet service factor only needs to be applied for fasteners being used in service in a wet condition. True or false? So closing the poll now, we'll see what our answers are. 47% said true and 53% said false. I will now turn it back to Bob. We will get back into his slides, and Bob will let you go ahead and answer that question and then continue forward with your presentation.
The answer to that question was false. So you need to consider reductions, obviously, and commonly when the wood in-service condition is going to be wet. But there are times you need to consider a moisture reduction factor when it's an in-use dry service condition if the fastener was installed in wet wood, where the wood may be shrinking away, reducing the capacity of the connector. So that's the important consideration takeaway, from that slide. So continuing where we were, discussing group action factors. A big factor in determining the group action factor is determining the number of rows, which can be tricky a little bit. So here are some diagrams to exist. Where fasteners in adjacent rows are staggered and the distance between adjacent rows is less than 1/4 the distance between the closest fastener in adjacent rows measured parallel to the rows, the adjacent rows shall be considered as one row for purposes of determining group action factors. For groups of fasteners having an even number of rows, this principle shall apply to each pair of rows. For groups of fasteners having an odd number of rows, the most conservative interpretation shall apply, which is figure 11b. So if you're inclined, we mentioned you can go through the equation, and here's the calculation to determine the group action factor, which is again quite cumbersome with a lot of variables. Preferably, or alternately, you can choose to use the NDS tables, which again does some of the work for you. So using the table 11.3.6a, you can look up your group action factors. Detailing provisions are given diagrammatically in the NDS for group fastener connections. Anything outside of these connections will require refactor calculation for edge distances, so it is usually best to detail connections that meet these requirements. Table 12.5.1a provides the end distance fastener requirements. Table 12.5.1b has fastener spacing requirements. Table 12.5.1c has the edge distance requirements, and 12.5.1d has spacing requirements between rows. But it is not always the connector that fails. The capacity of connections with closely spaced, large diameter bolts has been shown to be limited by the capacity of wood surrounding the connection. Connections with groups of smaller diameter fasteners, such as typical nailed connections in wood frame construction, may not be limited by wood capacity. Referring to NDS on multiple fasteners, these local stresses are addressed in section 12.6.3 and section 11.1.2, which states one method for determining these stresses provided in Appendix E. Section 11.1.2 noted that local stresses can be considered using Appendix E as one method. Appendix E is listed as a non-mandatory, which means other methods deemed appropriate by the design professional can be used. However, for this presentation, we find that the method detailed in Appendix E is appropriate. So let's review these requirements and what we are checking. Appendix E leads the designer through the stress checks for the three failure modes: net tension, where capacity of wood through the cross-section fails; row tear out, where the individual rows tear out; and a group tear out, where a large section tears out. This is a combination of row tear out and net tension failure. That pretty much covers the concept of shear connections for connecting two members in single or double shear. However, there are other adjustments that still need to be considered for other type of connections. End grain factor adjustments are required when dowel fasteners are inserted into the end grain of the member for both withdrawal and lateral design. And diaphragm factors will also apply for diaphragm construction. The NDS also provides guidance for toe nailed connections. It is important to understand that toe nails only resist loads in certain directions and thus are not recommended when the load is applied from several directions. Now let us review some of the detailing and considerations for wood structural panel connections. We mentioned overdriving fasteners can reduce performance and must be field checked to assure design intentions are carried through. APA technical topic, Effective Overdriven Fasteners on Shear Capacity, TT-012, provides guidance on evaluating overdriven fasteners. With braced and shear wall designs becoming more important in the building codes, it is not uncommon that tighter nail spacing be specified. Typical nailing of wall sheathing is 6 inches on center along the panel edges and 12 inches on center in the field. With these designs, tighter nail spacing, such as 4 inches on center on the panel edges and 6 inches on center staggered nailing patterns are often required. Not staggering nails can cause splitting of wood. NDS and structural composite lumber manufacturers have minimum distances to be maintained when nailing into the edge of different products like LVL, LSL, and PSL. Splitting happens because wood is relatively weak perpendicular grain. The nails are too close together to start acting like a wedge. Along with this tighter nail spacing requirements, some of the increased likelihood of panel buckling due to the inability of the panel to expand in its environment. APA technical note on minimizing buckling of wood structural panel provides guidance in addressing these high-risk applications. These photos show good staggered nail padding on the right and good panel gapping. However, it also shows the buckling that can occur from panel expansion when restrained by the nailing and not allowing the 1/8 inch gap that is normally required to work. Along with the additional nailing requirements for sheathing in high wind or seismic events, the connection of walls to the foundation has become more critical. In high wind and seismic zones, large plate washers are required to prevent splitting of the sill plate resulting from cross-grain tension stresses. These plates often use a slotted hole to allow them to be appropriately positioned on the sill plate. Adhesives are often used in addition to fasteners to bond wood subfloor to joist assemblies. This adhesive helps eliminate floor squeaks, and the bond creates some composite action between the joist and subfloor that increases the stiffness of the floor system. You can consult APA's Design Construction Guide, Residential and Commercial, for additional details and a description of the APA glued floor system. In typical building construction, gluing is often done of floor assemblies, but never of wall and roof assemblies for ductility reasons. Floor assemblies benefit from development of composite action between the subfloor sheathing and the joists to increase floor stiffness and reduce squeaks among components. APA provides a full description of this in the APA Design Construction Guide. As we mentioned earlier, the environment plays an important role in connection design. It's particularly important in harsh environments where corrosion of the connection needs to be considered. So what does the IBC say about corrosion-resistant connectors for preservative-treated wood? Well, the first thing we notice is that preservative-treated wood and fire-retardant treated wood are separate. And within FRT, fire-retreated wood, exterior-interior applications have been split. Looking at the exterior applications for pressure-treated and fire-retarded treated wood, the coating properties for pressure-treated and fire-treated wood exterior are similar, but shall be hot-dipped, zinc-coated galvanized steel, stainless steel, silicone, bronze, or copper. A minimum of ASTM A695 Class 55 minimum. The coating types and weights shall be in accordance with the connector manufacturer's specification. And in the absence of manufacturer's recommendation, a minimum of ASTM A653 Type G 185 for pressure-treated exterior applications shall be applied, or Section 2304 10.5.3 for fire-retarded treated wood for interior applications should be applied. Seems so simple and straightforward what the IBC is telling you to do, but unfortunately it's not always so straightforward. So I think a little basic understanding of what causes corrosion and how will help us how to deal with it. Some causes of corrosion include dissimilar metals, the environment, salt air, fumes, fertilizers, de-icing salts, and the preservative treatment of the wood itself related to dissimilar metals. So let's take a look at dissimilar metals. Corrosion can be induced when two dissimilar metals are coupled in a corrosive electrolyte. If we look at this galvanic corrosive table, when the two metals are placed together, one will act as a cathode and one will act as an anode. This results in the anode corroding. The farther apart the two materials are on the table, the greater the galvanic action, resulting in quicker corrosion. If you look at the table, stainless steel is far away from zinc. This is why using stainless steel fasteners should never be used with a galvanized steel connector. The zinc will act as an anode and corrode, leaving the steel protected. This is something that commonly see a field change where somebody wants to improve a connection by using a stainless steel nail with the off-the-shelf zinc hanger. It's a recipe for a disaster. Similarly, copper can interact with steel. This is why higher concentrations in the wood preservative can require a more robust connector, such as stainless steel. The fact is, corrosion does occur, and almost all materials should be expected to deteriorate with time when exposed to the elements. Although all metals shouldn't be expected to corrode at the same rate, there are some statements that are generally accepted as facts. Moist air is more corrosive than dry, hot air is more corrosive than cold, hot water is more corrosive than cold water, polluted air is more corrosive than clean air, Acids are more corrosive than bases. Salt water is more corrosive than fresh water, and stainless steel will generally outlast ordinary steel. This is where the designer needs to evaluate the environment to determine if the conditions exist when specifying a connection. Thank you very much for attending today. At this point, I'm going to turn it back over to Karen, who's been monitoring questions throughout the session to see if we've had any come in that we have time to address.
Thank you, Bob, and thank you everyone for hanging in there. As I mentioned before in our poll question, we will be creating a recording with the full set of slides and Bob's audio so that if any of you had any technical difficulties looking at the poll as Bob was progressing through the presentation, that will be rectified in the recording. So stay tuned for that. We will also be sharing a copy of this question and answer session. So if we don't get through all of the questions in our time together now, we will be posting the rest of those questions and answers after the fact. So without further ado, let's get into our technical questions. And one more housekeeping, there was a lot of requests for the slides. We will make a handout of the slides available after this session. So to the technical questions, let's see. Can you use a split ring and shear plates with SCL and glulam beams?
Okay, that's a good question. That's a connector we didn't go over today. NDS does have some guidance on that. And generally, you can use the split rings, and the shear plates easily with glulam beams. However, what I would mention is the use of split rings with structured composite lumbers like LVL. It's a little inconsistent with manufacturers, even as we discussed for the side-loaded connections, how that was different per manufacturers. It's a little inconsistent. So if you want to use those type of specialized connectors, I would recommend that you consult with the manufacturer of the SCL product that you're looking to use and get their guidance on how to design and specify using those connectors.
Thank you, Bob. Can I use screws in place of prescriptive nail patterns specified in the IRC when installing wood structural panels?
Yeah, we didn't go into a lot of panel detail connections, but yes, you can. However, when using screws, you should choose a screw that first has a size equal to or greater than the recommended nail. The untreated shank under the head of the screw should extend beyond the thickness of the panel, ensure that the panel is pulled securely against the framing. So we talked a little bit about that clamping action. Same thing with the screw. That's what the unthreaded portion for, is to make sure that that panel gets pulled down. Then we'd also recommend choosing screws from a manufacturer that can provide an evaluation report, like an ICC ES report from a qualified third party, with the approved application and design values. A cautionary note that I'd always mention when anybody ever asks me about using screws is that you should not be using drywall screws in any structural connections. They tend to be quite brittle and the heads break off, so they really should never be using any of the connections that we discussed today.
Great. You showed glulam and LVL multiply connections that showed using through bolts. Are screws like Simpson SDS or USP wood screws acceptable?
Okay, that's another good question. As we mentioned, that more molded connectors can be preferred over using large connectors. So that's where these screws come in. We're talking about a lot of small connectors, maybe than big half-inch bolt. So the use of screws or nails can accommodate this, and sometimes and often are preferred. The proprietary screws that you mentioned, they're proprietary, and we didn't cover them specifically in this presentation, because of that, but they are likely appropriate. I would encourage consulting with the structural composite lumber manufacturer and the screw manufacturer for details and capacities for those connections. They have similar charts to what I showed for the LVL connections with bolts, but they will have them with screws. And as I talk about this connection, something else is coming to mind that I'll just expound on. That's the use of carriage bolts. Over the years, I've seen carriage bolts often specified, often used in multiply connections. So, I'd like to just mention the carriage bolts do not conform to the ANSI ASME standards, the B18.2.2. The provisions of the 2015 do not apply to those bolts. So these bolts, while they may have the connection, they really don't fall under the NDS guidelines. So none of those numbers or those formulas really apply. However, use of carriage bolts, can be permissible in accordance with the standards, providing that you use the characteristics of the carriage bolt, including bolt material, bending strength, diameter, and consider that square neck under the head. It's quite easy to suck those carriage bolts into the side of the wood when you're tightening those down, since they don't typically have the same washer size that you would use with a standard bolt. So there's a cautionary tale. If it was me, I would really avoid the use of carriage bolts in any of these connections rather than try and make one work.
Okay, thank you, Bob. And another question that's related to multiply connections. It says you showed the examples that appeared to be for uniform loads. What do I do if I have another large beam hanging off of a multiply beam?
Okay, so the tables we looked at, they were for uniform loads. You're correct in that. But quite often you have heavy concentrated loads from other flush members, and they present different challenges to ensure that the point load is carried through to all the plies of the supporting member. It will require some design considerations. First, what type of hanger are you using? Are you using a top mount flange hanger where it may distribute load to all the plies, 2 plies out of 4? That can be a consideration. If using a face mount hanger to the fasteners penetrate all plies, some of those proprietary screws we discussed, can go quite long, and that might allow it to take the load into the other plies. So once these factors are considered, you may need to provide some supplemental connection as part of the hanger with additional fasteners, be it the screws or bolts, in close proximity to ensure that the loads are transferred between the plies. These can be designed using NDS designs for dowel bearing connectors. Alternately, you can consider using the proprietary screws that we talked about to distribute between plies. In the case of LVL, I'd first consult manufacturers' literature, as many of the manufacturers do provide some guidance on designing this detail for you.
Okay, I think we have time for one more question. You mentioned that the temperature factor was to be used when the sustained temperature was above 100 degrees. Does this apply to fire-resistive construction, or does the heat of the fire affect the allowable stress design values of wood?
Okay, that's a really good question. I used to get this often, getting consulted on a project that was involved with a fire. I got to take these stress reduction temperature factors. Those factors, as I mentioned, they were for sustained loading. Unfortunately, the fire-resistant design construction is very involved, and it's beyond what we're covering today. You can consult the Chapter 16 of the 2015 NDS and American Wood Council Technical Report number 10, calculating the fire resistance for exposed wood members, that can be found on American Wood Council's webpage for additional information. So that's a resource if you're trying to deal, with a post-fire event on how to really address that type of connection.
Thank you, Bob. Before we conclude, I'd like to touch on 3 quick things related to a short survey, CEUs, and upcoming webinars. We'd really appreciate receiving your feedback via the survey that you'll receive shortly, so please take a minute and fill that out. Also, don't forget to download the AIA or ICC Certificate of Completion from the links in the follow-up email that will be sent to you an hour after the webinar ends. And finally, make sure that you're signed up to receive our APA Update newsletter so that you'll be notified of our next webinar, Meeting the Energy Code Using the Performance Path, on August 23rd, as well as future webinars and updates to APA publications and standards. To receive it, all you need to do, starting from the home page of our website, is to click on the Sign In the upper right-hand corner of the page, and in the menu that drops down, simply select Register. From there, you'll need to let us know what you'd specifically like to receive, which in this case is the APA Update newsletter. I should mention that if you have technical questions on any topic related to the use of engineered wood products, don't hesitate the APA Help Desk, as shown here. And we also have field staff available to assist design professionals, builders, and code officials. Their individual contact information can be found on our APA website, apawood.org. Please feel free to reach out and take advantage of this resource. As mentioned earlier, a recording of today's webinar and the answers to the questions that were asked will be posted at apawood.org in a week or 2. And with that, I'd like to thank you for attending. Have a great day.